In this video, let us discuss the explicit finite difference method for option pricing. The valuation of derivative securities stands as a cornerstone of modern quantitative finance, a field revolutionized by the seminal work of Fisher Black, Myron Searles, and Robert Merton in the early 1970s. The derivation of a partial differential equation governing the price of an option provided a theoretical framework that transformed financial markets. The Black-Scholes Merton model culminates in a partial differential equation that describes the price of a European-style derivative, denoted by CST, as a function of the underlying asset's price S and time t. The equation is given by this formula. The partial derivative of C with respect to t plus r into S into partial derivative of C with respect to S plus half into sigma square into S square into second order partial derivative of C with respect to S minus RC is equals to 0. Here, R represents the constant risk-free rate and sigma is the constant volatility of the underlying assets returns. The financial intuition underpinning this equation is profound. It arises from the principle of no arbitrage, which posits that in a frictionless market, it is possible to construct a portfolio consisting of a position in the derivative and a continuously rebalanced position in the underlying asset that is perfectly hedged and therefore risk-free. The return on this riskless portfolio, by definition, must be equal to the risk-free rate of return. This equilibrium condition gives rise to the PDE. Each term in the equation has a direct financial interpretation corresponding to the Greeks, which measure the sensitivity of the options price to changes in the market parameters. The partial derivative of C with respect to t is theta, representing the rate of time decay of an options value. The partial derivative of C with respect to S is delta, which measures the rate of change of the option price with respect to the price of the underlying asset. The second order partial derivative of C with respect to S is gamma, which represents the rate of change of delta with respect to the underlying stock's price. From a mathematical standpoint, the Black-Scholes equation is a second order linear parabolic differential equation. More specifically, it is classified as a convection diffusion equation, a type commonly found in physics and engineering to model phenomena involving both transport and spreading. The term involving the first spatial derivative, Rs delta C by delta S, is a convection or drift term, while the term with the second spatial derivative, 1 by 2 sigma square S square into second order partial derivative of C with respect to S, is a diffusion term. The critical feature of Black-Scholes PDE is that it is a backward parabolic equation. This distinguishes it from typical physical models like the heat equation, which are forward parabolic. In a forward problem, a system state is known at an initial time, and the equation describes its evolution into the future. In option pricing, the definitive condition is not known at the beginning, but at the end of the contract's life, the time of expiration t. At this point, the options value is simply its intrinsic payoff. The valuation problem is therefore to determine the option's fair price today, given this known future boundary condition. This requires solving the PDE backward in time, from time t to the present. This backward-looking nature is not merely a mathematical convention. It is the computational embodiment of the core financial principle of valuation, which involves determining the present value of a known future cash flow by discounting it through time according to a specified dynamic process. For standard European call and put options under the model strict assumptions like constant volatility and interest rates and no dividends and more, an elegant analytical solution exists, which is the renowned Black-Scholes formula. This closed-formed solution provides a direct and efficient way to calculate the option price. However, the financial world is filled with derivative contracts and market conditions that violate these idealized assumptions, rendering the analytical formula inapplicable. Numerical methods become indispensable in these more complex and often more realistic scenarios. In one of those scenarios, we have American options. These options can be exercised at any time up to and including the expiration date. The possibility of early exercise introduces a free boundary problem, which prevents a simple closed form solution. Numerical methods are required to decide at each point in time for each asset price whether holding the option or exercising it is optimal. The next scenario is the case of exotic options. Many options have complex payoff structures or part dependencies, like barrier options and Asian options. These features are not tractable with analytical formulas. Next, we have advanced models, where real-world asset dynamics often exhibit features like stochastic volatility or jumps. Models incorporating these features, such as the Heaston or the Bates models, lead to more complex PDs for which analytical solutions are rare. Similarly, models that account for the transaction costs often result in nonlinear PDs. In all these cases, finite difference methods provide a powerful and flexible framework for finding a solution, By discretizing the continuous PDE, FDM transforms the problem into a simple system of algebraic equations that can be solved on a computer, offering a robust path to evaluation where analytical methods fail. The fundamental idea of finite difference method is to approximate the continuous domain of the problem with a discrete grid or lattice. For the Black-Scholes equation, this involves creating a two-dimensional grid spanning the dimensions of the asset price and time t. The continuous variables are replaced by a finite set of discrete points on this grid. The partial derivatives in the PDE are then replaced by finite difference approximations, which are algebraic expressions involving the values of the solutions at the neighboring grid points. This process effectively converts the differential equation into a large system of linear algebraic equations. The solution algorithm proceeds via time marching procedure. As established, the problem is defined by a known condition at the final time t. The FDM algorithm therefore begins at the terminal boundary, where the option value at every node on the grid is set to its known payoff. It then steps backward in time, one discrete step at a time, using the system of algebraic equations to compute the option values at the previous time levels, based on just the computed values at the current levels. There are three primary schemes for implementing this backward march, each with distinct characteristics regarding stability, accuracy, and computational complexity. The first is the explicit method, the simplest scheme where the value of the future grid node is calculated directly from a small set of known neighboring nodes. It is intuitive and easy to implement, but suffers from the conditional stability. The next method is the implicit method, a more robust scheme where the value at each node depends on several other unknown nodes at the same time step. This requires solving a system of linear equations at each time step, but is conditionally stable. The next is the Crank-Nicolson method, a hybrid approach that averages the explicit and implicit schemes. It is also unconditionally stable and generally offers a higher order accuracy, making it popular choice in practice. Today, we'll proceed with a detailed derivation and analysis of the first of these, the explicit finite difference method, laying the foundational groundwork necessary for comprehensive understanding of numerical option pricing. The first step in applying any finite difference method is to transition from the continuous world of the partial differential equation to a discrete computational domain. This involves constructing a finite grid and defining algebraic approximations for the derivative operators that form the building blocks of the PDE. The Black-Scholes PDE is theoretically defined over an infinite domain for an asset price S. For computational purposes, this domain must be truncated and discretized. The asset price domain is bounded by choosing a sufficiently large maximum price, S max, which the underlying asset is highly unlikely to reach before the option's expiration. This truncated domain is then divided into m equal intervals. The size of each price step or spatial resolution is therefore S max by m, which is equal to delta S. Now, the time to maturity domain is calculated similarly by dividing it into n equal intervals. The size of each time step will be t by n, and this is equal to delta t. This process creates a two-dimensional grid or mesh of discrete points. A specific point on this grid can be identified by a pair of indices I, j, where I is the index of the asset price ranging from 0 to m. The asset price at index I is Si equal to I into delta S, and j is the index for time ranging from 0 to n. The time at index j is tj and is equal to j into delta t. The goal of the finite difference method is to approximate the value of the option cjt at each of these grid points where cji is approximately equal to c of si, tj. The choice of S max is a non-trivial modeling decision. A value that is too small will introduce a significant error from the artificial boundary, while a value that is too large can adversely affect the stability and efficiency of the explicit scheme. The heart of the finite difference method lies the replacement of continuous partial derivative with discrete algebraic approximations. These approximations are derived from the Taylor series of expansion of a sufficiently smooth function f of x around the point x. A Taylor expansion of f of x plus h and f of x minus h are f of x plus h is equal to f of x plus h into first derivative of f of x plus h squared by 2 factorial into second order derivative of f of x plus h cubed by factorial of 3 into third order derivative of f of x plus big O of h4. Now, f of x minus h is equals to f of x minus h into first order derivative of f of x plus h squared by 2 factorial into second order derivative of f of x minus h cubed by 3 factorial into third order derivative of f of x plus big O of h to the power of 4. By rearranging these expansions, we can derive approximations for the first and second derivatives with varying orders of accuracy. First, let's look into the first derivative approximations. By truncating the first expression after the linear term and solving for f dash of x, we obtain the forward difference formula, which is equal to derivative of f of x is equal to f of x plus h minus f of x by h plus big O of h. This approximation has a truncation error of order big O of h, meaning it is first order accurate. Similarly, using the second expansion gives the backward difference formula, which uses the point itself and the point behind it. Therefore, the derivative of f of x is equal to f of x minus h by h plus big O of h. This is also first order accurate. Now, a more accurate approximation can be found by subtracting the second expansion from the first and solving for f dash of x. This cancels the even powered derivative terms, giving us derivative of f of x is equal to f of x plus h minus f of x minus h by 2h plus o to the power of h square. The central difference formula is second order accurate and is therefore generally preferred for spatial derivatives when possible, as it converges to the true value more rapidly as step size h decreases. Now let's look into second derivative approximations. To approximate the second derivative, we add the two Taylor expansions. This cancels out the odd power derivative terms, resulting in the central second difference formula, which is f double dash of x is equal to f of x plus h minus 2 f of x plus f of x minus h by h square plus o of h square. This approximation is also second order accurate. The choice of which approximation to use for each derivative in the PDE is what defines the specific finite difference scheme. The explicit nature of the scheme arises from a specific combination of these approximations that allows the unknown value of the next time step to be calculated directly from the known values of the current time steps. For the Black-Scholes equation, which is solved backward in time, we evaluate the spatial derivatives at the known time level j to compute the unknown values at the previous time levels j minus 1. The chosen approximations for the explicit scheme at gender grid points Si and Tj are as follows. For time derivative, which is partial derivative of c with respect to t, a forward difference approximation is used with respect to the calendar time. Since the computation proceeds backward from j is equals to n to j is equals to 0, this corresponds to a backward difference on the computational grid. Therefore, the formula for time derivative is partial derivative of c with respect to t is approximately equal to c of ij minus c of ij minus 1 by delta t. This is a first order accurate approximation of the order O, big O of delta t. Next, we approximate the value of the space derivative, which is delta c by delta s. A central difference approximation is used to leverage its superior accuracy. Therefore, partial derivative of c with respect to s is approximately equal to c of I plus 1 j minus c of I minus 1 j by 2 into delta s. This is a second order accurate approximation of the order big O of delta s square. Now we calculate the second order space derivative using the central second difference approximation, resulting in second order partial derivative of c with respect to s is approximately equal to c of I plus 1 j minus 2c of ij plus c of I minus 1 j by delta s square. This is also a second order accurate approximation. This particular set of choices, evaluating all spatial derivatives at the known time level j, is the defining characteristic of the explicit method. It ensures that when these expressions are substituted into the PDE, the only term at the unknown time level j minus 1 is Cij minus 1, allowing it to be solved for directly. With the grid structure and derivative approximations established, the next step is to substitute these discrete forms into continuous Black-Scholes PDE. This process transforms a differential equation into a recurrence relation that can be solved computationally. As we discussed earlier, the Black-Scholes PDE is partial derivative of c with respect to t plus r into s into partial derivative of c with respect to s plus half into sigma square into s square into second order partial derivative of c with respect to s minus rc is equals to 0. We substitute the finite difference approximations like we discussed earlier at the grid point s of I, comma t of j, which is denoted by I, comma j. The value of asset price at this point is s of I is equals to I into delta s. This is the resulting discrete equation. This equation holds for all interior nodes of the grid, that is, for I is equals to 1, 2, 3, and so on till m minus 1. and for each time step j, which is equal to n minus 1 and so on till 1. It is an algebraic relationship that links the unknown option value at time tj minus 1 to three unknown option values at the later time tj. The defining feature of the explicit method is that the unknown value can be isolated easily. We rearrange this discretized equation to solve for Cij minus 1. First, we move all terms except the time derivative to the right-hand side. This will give us this equation. Now we multiply the right-hand side with minus delta t and move the Cij to the right-hand side to isolate the Cij minus 1 term. This will result is in this equation. Now we group the terms by the known values at time level j. After grouping terms by Ci minus 1j, Cij, Ci plus 1j, we get the coefficients for Ci minus 1j as alpha I is equals to delta t into half into sigma square I square minus half Ri. And then we get the coefficient of Cij, which is equal to beta I is equals to 1 minus delta t whole into sigma square I square plus R. And we get the coefficient for Ci plus 1j as gamma I is equals to delta t into half into sigma square I square plus half into Ri. The sum of these coefficients is equal to 1 minus r delta t, which corresponds to the discount factor over a small time interval delta t, the risk-free rate r. The coefficients correspond to the risk-neutral probabilities of moving down, staying, or moving up in the asset price grid during one step, reflecting a trinomial tree analogy. They depend on the spatial index I because of the S and S squared terms in the Black-Scholes PDE and the uniform discretization of asset prices. Stability requires these coefficients to be non-negative, which possesses constraints on delta S, delta T, sigma, R, and the grid spacing. The final explicit the final explicit update rule with coefficients is equal to C of I j minus 1 is equal to alpha I C of I minus 1 j plus beta I C of I j plus gamma I C of I plus 1 j. This completes the algebraic formulation and interpretation of the explicit finite difference method. While the explicit method is typically implemented with a simple iterative loop, expressing it in a matrix form is invaluable for formal stability analysis and for drawing comparisons with other finite difference schemes. Let Cj be a column vector containing the option values at all interior spatial nodes at time step j, where Cj is equals to C of 1 of j, comma C of 2 of j, comma C of 3 of j, so on till C of m minus 1 of j. The system of update equations for all these interior nodes can be written as a single matrix vector multiplication. C of j minus 1 is equal to A of Cj plus B, where here A is an m minus 1 into m minus 1 tridiagonal matrix, whose entries are coefficients derived from above. This tridiagonal matrix looks somewhat like this. The vector B is an m minus 1 dimensional column vector that incorporates the known values from the boundaries at time step j. The first element Cj minus 1, which is Cj minus 1 of 1, depends on C0 of j, C1 of j, and C2 of j. Since C0 of j is a known boundary value, its contribution alpha 1 C0j is moved into the vector B. Similarly, the last element Cm minus 1 j minus 1 depends on the known boundary value Cmj. So its contributions gamma m minus 1 Cmj is also placed in B. All other elements of B are 0. So B will look something like this. This matrix formulation elegantly encapsulates the entire time stepping procedure. The backward march from time t to 0 corresponds to repeatedly applying this matrix transformation, starting with the known vector of terminal payoffs. The stability of this entire process hinges on the properties of the amplification matrix A. In explicit FDM, the update for each grid node at time step j minus 1 is a weighted sum of the neighboring values at the time step j. So the time step delta t must be sufficiently small so that the errors are damped rather than magnified as computation moves backwards. For the Black-Scholes equation, a typical explicit FDM stability condition is delta t should be less than or equal to delta s square by sigma square into delta s square max. If the stability condition is violated, the grid values can blow up. Now, let's translate the mathematical framework of explicit finite difference method into a practical working implementation using the Python programming language. In this code, we use vectorized operations, which significantly improves the performance compared to the standard Python loops. This implementation will price a European call option. First, we import NumPy for numerical calculations and norm from SciPy for the normal cumulative distribution used in Black-Scholes formula. Next, we define a function for analytical Black-Scholes price of a European call option. In the function, we calculate D1 for Black-Scholes formula, a risk-adjusted measure of relative stock by strike. And then we calculate D2, which incorporates volatility and time. At last, we compute the call price based on the Black-Scholes formula and return the computed price. And we define a function to calculate the price of a call using explicit FDM. The first step is discretization. In this step, we calculate the grid size, dt and ds, where dt for the time steps and ds for the asset prices. Next, we check for the stability condition of dt we discussed earlier, and which ensures that dt is small enough for explicit FDM to be a stable per derived condition and warns if the stability is violated. Now, we initialize the grid, where svec contains asset prices and grid holds the option values for each asset time pair. After this, we calculate the boundary and terminal conditions. This line sets the intrinsic values at the final time t for the call option. The boundary condition for at step s is equals to 0 is when the option is worthless and is equal to 0. Now, after this, we calculate the boundary condition at s max, where we use the discounted value of s max at each time step. Now we proceed to the backward induction process of the finite difference. We construct arrays of coefficients for weighted update formula that reflects the Black-Scholes discretization. The I-vec is a vector of spatial grid indices ranging from 1 to m-1. The alpha-vec, beta-vec, and gamma-vec define, for each node, the weight assigned to the values at grid I-1 j plus 1, grid I j plus 1, and grid I plus 1 j plus 1, respectively. This embodies the explicit FDM formula, which is Cij is equal to alpha I Ci minus 1 j plus 1 plus beta I Ci j plus 1 plus gamma I Ci plus 1 j plus 1. The coefficients depend on the node index because volatility and drift terms scale by I and I square. Now we loop backwards in time through the grid. We traverse all time steps from expiry back to the present, updating option values at each asset grid node from previous time level. For each time step j, this loop updates the option prices at all interior asset nodes I is equals to 1 to m minus 1. Further time using values at the next time step j plus 1. We use vectorized operations where each interior strip of the grid is updated simultaneously. At last, we extract the final computed option value at the specific initial asset price S0. If S0 does not align perfectly with the grid node, we use linear interpolation to estimate the value using neighboring nodes. This ensures that the return price closely matches the theoretical starting price even when the grid spacing is coarse. At last, we return the price. Now, here we initialize the parameters with initial price or S0 is equals to 100, strike price is equals to 100, time to maturity is equals to 1 year, the risk-free rate is 5%, and sigma is equals to 20%. Always note that n must be large enough to satisfy the stability because a larger n brings out a smaller delta t. We initialize m is equals to 100 and n is equals to 25,000, and S max is equals to 2 times the strike price. Now we show the FDM price, which is the result of sending these parameters into the explicit FDM European call function. And we store the analytical price, which is the price we got from the analytical Black-Scholes model. So if we run this code, this is the result we got. The explicit FDM price is 10.44073, and analytical Black-Scholes price is 10.45058. The pricing error is very, very, very small and somewhere around 0.00986. The explicit finite difference method provides a foundational and pedagogically valuable, showing how accurate the explicit finite difference method is in calculating the option price. The explicit finite difference method provides a foundational and pedagogically valuable approach to solving the Black-Scholes partial differential equation. Its step-by-step nature illuminates the core principles of numerical option pricing. In conclusion, the explicit finite difference method serves as an indispensable entry point to the world of numerical PDE solutions in finance, while its practical utility is often superseded by the more robust and efficient implicit and Crank-Nicolson schemes. The lessons learned from its derivation, stability analysis, and implementation provide the essential concepts and cautionary tales that inform the intelligent application of all finite difference techniques in quantitative finance. Thank you.